Okay. Yeah, welcome everybody to this new session of seminar in Equivariant bodies and application. Today we have the pleasure to have Renee Hoekzema from the University of Oxford. I see that she's an artist. She works in paleontology and physics. Yeah. So she will talk about Schneiden and Kleven, cut and paste invariants on manifolds and relation to cobordism. Yeah, thank you very much.
Thank you. Thanks so much for the introduction. I'm now in Amsterdam, actually. I was forever in Oxford, but I have sort of managed to leave. So thanks so much for inviting me to give this talk. So this is all joint work with Mona Merling, Laura Murray, Carmen Rovi, and Julia Sinikina. So I know that some people were also at the conference at Oaxaca, so I've sort of tried to make the talk understandable for everyone, but also sort of present some disjoint parts of the work. Right, so it all goes back. Can people see my cursor, by the way? Okay. Right, so the ideas will go back to very, very classic mathematics of scissors congruence. People asked a very, very long time ago the question, if I have two polygons P and Q, is it possible to cut P into pieces and reassemble them to form Q? And it turned out it was shown very early proof in the start of the 19th century. Yes, I can do this whenever I have the polygons have the same area. So there's a very nice constructive proof. I can take a polygon. I can always cut it into triangles. Then those triangles I can make into rectangles. Those I can make into rectangles of a given width. And then I can stack them and form like a square of that same area. So I can go from any polygon to any polygon with a square of the same area, and then I can also go back. So this gives me a sort of nice constructive proof. So Hilbert in 1900 posed a question of what happens in higher dimension, in particular in dimension 3. So given two polyhedra P and Q of equal volume, are they equally composable, so made out of the same bits? And his motivation, particularly for this question, was that there's like an argument for it, like you can show that the area of a pyramid is base area times height divided by 3, using all kinds of like exhausted or infinitesimal methods. But it'd be nice to just take a tetrahedron and cut it up into a certain number of cubes, and then say, well, that means that the volume is this number of cubes. So this was actually the first of Hilbert's problems to be solved by a student Dane in 1901 in a negative. And what he did was the following. So he said that, well, we have certain sort of things that are conserved if we are cutting polytopes. If we would cut like across an edge, then the sum of the length of what that edge was before is preserved. If we cut along an edge, then the sum of the angles is preserved. And we might sort of cut somewhere in the middle and create a new edge, but then we created it out of either like in the interior or on the face. So the angles, the dihedral angles, have to add up to a multiple of pi. So you show that the Dane invariant is preserved, which is the sum over all edges of the length of the edge tensor the dihedral angle. I think I want to say up to z pi. So for example, if we take a cube, then all the dihedral angles are pi over 2. So I get that the Dane invariant is 0. Whereas if I take the regular tetrahedron, then the dihedral angle is the arc cosine of a third, which you can show is not rational. So in particular, if I compute a Dane invariant, this term can have to be 0, and therefore this is non-zero. So this is an easy argument to show that a regular tetrahedron is not equity composable or not scissors congruent with a regular cube. So just some nice sort of side notes. This is an interesting area that's still like active. There are also rational tetrahedra that do have Dane invariant 0. So it's not a sort of combinatorial thing. It's really about the geometry of that polytope. And there was recently a classification of these rational tetrahedra. And also, like, if Dane invariant is 0, then this is necessary but not sufficient condition for tessellating R3. So these are sort of interesting areas, just as a side note. And Seidler showed in 1965 that indeed, if I have the same volume and the same Dane invariant, then polyhedra are cis-congruent. So now, of course, we want to ask the question in general dimension. So I can define SCN of X to be the Grothendieck group of polytopes in X to the n, where X is maybe the reals or a hyperbolic space up to cis-congruent. And so I can, in the settings, I can generalize the Dane invariant to higher dimensional Dane invariants. And it was shown in 1972 by Jessen that this higher Dane invariant in the 4 volume that suffice to describe the cis-congruent group in four-dimensional Euclidean space. However, in higher dimension, Euclidean space is still open, and also in hyperbolic or spherical geometry, this is still open for dimensions 4 and higher. So very recent mathematics sort of is trying to approach this question again, or at least like working with the cis-congruence groups. So Campbell and Zakharevich they built a K-theory spectra that recover these cis-congruent groups on pi knots using things called assemblers and subtractive categories. So this is really like a categorification of these cis-congruent groups. There's higher homotopy groups of such a spectrum, which sort of generalize or sort of categorify these cis-congruent groups. And very recently, Kari Malkovich, just this month, showed that cis-congruent K-theory, so the spectra built using their machinery, is a Thom spectrum. So there's sort of some hope to compute things about these higher cis-congruent groups. So our setting is that of a different kind of cis-congruence, which is manifold cis-congruence. So cutting and pasting of manifolds. So I call two manifolds M and M prime SK equivalent for schneiden und kleben, which is German for cut and paste. If I can write M as two pieces M1 and M2 glued along the boundary over phi, and I can write M prime as the same two pieces but glued along a different diffeomorphism over the boundary. Okay, so I can think of, like, I have a manifold, for example, 2 tori. I cut along a codimension 1 sub manifold with trivial normal bundle, and I glue back differently to get, for example, a sphere and a 2-hole torus. So now I'm going to find SKN to be n-dimensional manifolds up to SK equivalents. And this is an abelian group where disjoint union is the operation. So here, all my manifolds are going to be compact and oriented. And in this case, I'm talking about closed manifolds and no boundary. So for example, if I take one-dimensional manifolds, the compact ones are all generated by the circle. And the circle I can cut, and then I can glue back 2 circles. So in particular, I see that the generator of this monoid is sent to 0. So SK1 is 0. And it turns out that actually cutting and pasting is very strong in general. So this group is 0 whenever the dimension is odd. And I have 2 invariants in general. I have the Euler characteristic and I have the signature.
Okay.
So just, going back to these examples in dimension 2, I can get a torus and glue 2 tori, or I can get these 2-hole torus and glue a sphere and a 2 tori, glue a 2-hole torus. And this is just the equations the Euler characteristic is 0, so I can make more of these things, or the Euler characteristic is 0 is the same as 2 minus 2. So of course, I'm sure people here are interested in a different kind of equivalence of manifolds, which is that of cobordism. So the pair of pants, everyone's favorite cobordism, also witnesses that one circle is coborded to two circles. So we can ask the question, what are the relationships between these two equivalence relations of manifolds? So it turns out if I define omega n to be n-dimensional manifolds up to cobordism, also as a B-link group with this union, there's no map either from skn to omega n or the other way around. But I can take the common quotient, which is sk bar n, so n-dimensional manifolds up to cobordism and sk equivalence. And I call this cobordism kind of paste invariants. And I can ask what the two kernels are of the canonical projection maps. And the kernels are as follows. So, of course, spheres are 0 in cobordism, but they have a non-zero Euler characteristic in even dimensions, so they're non-zero in SK. But if I kill them, then I get SK bar. Whereas for omega n, all mapping to Ra. So a mapping to Ra is easy to see is 0 in SK. So if I kill all mapping to Ra, then I get SK bar. So I actually, in terms of invariance, of course, like the Euler characteristic is an invariant of SK, but not of cobordism. But if I kill that one, then all that remains in the cobordism kind of paste invariance is a signature. So clearly, like these groups are quite simple in terms of what they amount to in terms of invariance. But it'd be nice, like, you know, perhaps we can build a sort of higher higher structures of manifolds out of them that would yield more interesting insights.
Excuse me, are you taking, are you assuming your manifolds are smooth?
Yes, everything is smooth. Did I, maybe that wasn't on my list. Yeah, so smooth and compact, and I was talking about closed manifolds here.
Thank you.
And oriented.
Sure.
So very, very nice. Okay, so our project was motivated by the following things. Firstly, the classical cis-congruence groups were lifted to a K-theory spectrum, as I mentioned before. Also, if you think about cobordism groups, they are connected components of a cobordism category, and the higher multiple groups of this cobordism category can be shown to equal the multiple groups of the Madsen-Tillman spectrum. So this is also sort of a categorification of these cobordism groups to like higher groups that have something to do with manifolds. So the goal was to define a K-theory spectrum that recovers these kind of based groups 1 by 0. So the first problem that we ran into is that, well, when we cut a polytope, as in cis-congruence, then the pieces are naturally polytopes. Whereas if I cut a manifold, then the pieces are manifolds with boundary. And if I do something with K-theory is really about like building things from smaller things. But all the things have to be in the same category, otherwise you get into trouble. So the solution is to work instead in the category of manifolds with boundary, and this is really sort of necessary in order to do this. So we define SK boundary to be n-dimensional manifolds with boundary up to SK boundary equivalence. So what is SK boundary equivalence? Well, I allow myself to cut, but I cut into the interior of manifold, not the boundary. And then I glue back everything that I cut. Okay. So in particular, this operation preserves the boundary that I had. And this is different from an SK boundary operation that was defined in the SK book by Harris, Cracknell, and Ossa. And we show that there's, this is sort of a minimal way of allowing boundary, in the sense that there's a short exact sequence from skn to skn boundary to like taking boundary. So obviously this boundary is preserved, so I can make a map to the group completion. So I'm taking group completion here because otherwise I don't get a group. And I here just go to the monoids of n-1 dimensional manifold. So just, yeah, I mean, maybe I don't really have time to go into detail. But yeah, it's a sort of nice little proof. So what we applied was what's called K-theory squares, which is a new formalism developed by Campbell and Zakharevich, which is really this is a formalism that generalizes Waldhausen K-theory. So you can recover Waldhausen K-theory, but in principle you can do more general stuff. So the input is something called a category with squares, C, and the output is K squares, which is an infinite loop space. So a category of squares is a category that has certain sort of commuting squares, which I identify as being distinguished. And certain squares are supposed to always be there, and I have certain conditions on like that I can compose these that I won't go into. And the output is an infinite loop space that is built using these squares. So K square of C is loops on the realization of a bisimplicial set, and this bisimplicial set is I send P and Q to like all the P times Q ways of composing these squares. And now what they show is that this infinite loop space satisfies something very nice, namely K0. So the pi naught of this infinite loop space, K squares, is spanned by the object of C up to a square relation. The square relation being that whenever I have a square A, B, C, D, I get the relation A plus D is B plus C. So you can really think of this as being sort of, well, if I have a push out, so I glue B and C over A, then in particular, D should be B plus C minus A. So this is sort of that relation. Okay, so how did we apply this? We built a category of squares of manifolds. So the objects of this category are smooth, compact, n-dimensional manifolds with boundary, again, oriented, etc. The morphisms are embeddings of manifolds that are nice in a way, and we call this SK embeddings. So what SK embeddings do is that every boundary component of the domain is sent either entirely to the interior or entirely to the boundary. And to the interior with as a top manifold with your normal bundle, so that we don't have sort of examples where we like hit like a piece of the boundary, but then go off it again. And then the squares in this category of squares are push-out squares. So not all push-outs exist in manifolds, but I just take the squares that are push-outs. So these are really squares that realize that I'm gluing two manifolds along a codimension 0 submanifold. So we show that this is indeed a category of squares with all the conditions, and this means that we get an infinite loop space, K squares of manifolds. And now the main theorem of the first paper is that K0 of this, so pi naught of this loop space, infinite loop space, indeed recovers SK boundary. So what, more or less the rough content here is that manifolds with boundary up to SK boundary equivalence is the same as manifolds with boundary up to the square relation, where a quotient by the square by A plus D is B plus C whenever I have such a square. So moreover, we've shown that like taking chains gives rise of a map of spectra from K square of manifolds to K of Z, which lifts the Euler characteristic on pi 0. So we have like sort of at least one map with which to understand the spectrum. But of course, it'd be nice to like understand more, and maybe hopefully it'd be nice if the spectrum would give us nice invariants on higher homotopy groups, for example. And one thing that we really like to do is to understand this link to cobordism. So I had these two short exact sequences before. And it'd be nice to understand these on the level of spectra, so lift these to spectral maps. So what we've done in follow-up work with Carmen Rovi and Julia Semikina is to build a spectrum that lifts SK bar boundary, which I have not defined yet, and lifts a canonical quotient map from SK boundary to SK bar boundary to map of spectra. And we do this using cubes of manifolds. So before, where we had squares, we now use cubes. Okay, so first, in order to define this question, I need to define what SK bar boundary is. So this is not entirely trivial because I'm now working with manifolds with boundary, and I want to quotient them both by an SK relation and by a cobordism relation. But if I use cobordism on manifolds with boundary, and I allow sort of free boundary to my cobordism, so here I have like an ingoing and an outgoing direction, but I have additional boundary, then this cobordism group is always 0, because I can very easily, I can take these two cylinders and have the ends be free, and this is a cobordism between two manifolds, a cobordism with boundary between any two manifolds. So what we want to do is we want to do something similar to what we did for the SK boundary case, which is preserve the boundary. So we use trivial boundary cobordism. So that's a cobordism that on the boundary is a mapping cylinder, so is diffeomorphic to an interval. So now we can define omega tilde to be the monoid of n-dimensional manifolds with boundary up this trivial boundary cobordism. Again, we have to group complete in order to make this a group. And if we do this, we have the following 4-term exact sequence. So the map from normal cobordism to trivial boundary cobordism has a kernel given by twisted doubles. And that's because of the following picture, really. So if my twisted double is M glued along the boundary with M with the opposite orientation, and if I take if I take an interval times such a twisted double, and I sort of peel it apart in the right way, what I get is a trivial boundary cobordism between the twisted double, disjoint union, the manifolds, to just the manifolds. Okay. So this is just in the monoids. This is just some relation. This is just a not against lift monoid. But then if I take the group completion, that means that my twisted double is going to go to 0. Yeah. I can't hear you, Doug.
Yeah, go ahead.
In that picture, shouldn't one of the M's at the bottom be M bar?
No, so that's about how you define what a cobordism between two things is. So if like normally you define a cobordism to have like on one thing you have like an orientation preserving diffeomorphism to the boundary, and then on the other thing you have orientation reversing diffeomorphism. So this endpoint is M bar, but then that means that it's a cobordism to M.
Okay.
Okay.
All right.
It's always confusing. It's like
yeah. Okay, thank you.
Okay, so now we can define SK bar boundary to be the group completion of n-dimensional manifolds with boundary up to SK boundary and trivial boundary cobordism relations. And it turns out that now actually taking the trivial boundary cobordism was already enough. So this is isomorphic. So it doesn't matter if I then quotient that by my SK boundary relation. And we get a nice short exact sequence. So if we quotient out normal cobordism by these mapping tori, sorry, twisted doubles are the same as mapping tori and cobordism. So here the top sequence is my former 4-point short exact sequence, the exact sequence to the short exact sequence. And I now have an isomorphism as follows. So like now I have a short exact sequence from SK bar to SK bar boundary to Cn-1. So that was similar to what we had before for SK boundary. So this shows again that this is really a sort of minimal way of extending SK bar to include manifolds with boundary. Okay, so this is just a summary of what I sort of went over. So now we want to categorify this group so that we get a spectrum that recovers on pi naught SK bar boundary. So whereas in the categorification of SK boundary, I had used squares of manifolds, I'm not going to use cubes of manifolds. So these cubes are going to be on the front and back face, they're going to be a cut and paste square as before. And then inward, I'm going to have trivial boundary cobordisms. And I'm going to have, in the middle, I'm going to have a cut and paste square, so push-out square of trivial boundary cobordisms. Okay, so this was like brief. I'm going to go through the definition in a bit more detail later. Just to already say what the result is. So remember for the bisimplicial set, I had k squares of manifolds. I defined this to be loops of the realization of this bisimplicial set. And then I had the k0 of this was isomorphic to SK and boundary. Now I define a trisimplicial space. So it really has to be a space in this case that sends P, Q, and R to always a composing such sort of fundamental cubes of manifolds. I define my cube K theory of manifold bar. This bar is sort of representing that we have a topological space now as loops on the fat realization of this trisimplicial space. And then the theorem is that on K0, so on pi naught of this infinite loop space, we indeed recover SK bar boundary. Okay, so how do we define this trisimplicial space? So first, there's always a question of how do I think about manifolds? Like, how do I actually sort of take a manifold, right, and like do something with it? So the way we're thinking about manifolds, which is very analogous to the way people think about manifolds in defining sort of topological cobordism categories, so we think of it as a subset of R infinity. And in this case, we want to define a manifold with boundary as a subset of R plus times R infinity. That's like a subset that is a submanifold in such a way that the boundary lies on 0 times R infinity. Okay, and we want the boundary to lie sort of nicely. We don't want it to be like tangential to this plane, but we want it to stick out. So we want to have introduce colors. So we call such a submanifold epsilon neat, or epsilon boundary neat. If in a sort of neighborhood of this plane, which is 0 times R infinity, my manifold is just cylindrical. So it's this interval times the boundary. So now in order to define sort of all images of my manifolds, or all sort of copies of my manifold in R infinity, I take manifolds that respect this color, embeddings that respect this color from my manifold into R plus times R infinity. But now I have embeddings. So embeddings means that like I've parameterized sort of, I can act by a diffeomorphism before the embedding. So I mod those out, those diffeomorphisms out, and that what I get here is like a moduli space of submanifolds of R plus times R infinity that look like my manifold M. And this is sort of what's called B-diff M, normally if you look at cobordism categories. So now, of course, I don't want to actually keep track of a specific color. So I want to let the color, like take a co-limit of the color going to 0, so that every manifold is ensured to have some sort of nice perpendicular color, but not of the same width. And then I take x0, to be the disjoint union of all diffeomorphism classes of manifolds of such moduli spaces of manifolds. So this is just a very complicated way of saying I take all manifolds with boundary, okay, n-dimensional manifolds with boundary. So for technical reasons, I also want to take the discrete topology on this space x0. So on the I'm defining what in the paper is x delta. Okay. So let's define the one simplicial directions. So I defined already before an SK embedding for phi from manifold M to N to be a smooth orientation preserving embedding, such that the components of the boundary of the domain, so the boundary of M, either go entirely to the interior of M as a submanifold of trivial normal bundle, or they go entirely to a boundary component of N. So these are called I call SK embeddings. I can make this into a space using C infinity topology. And I define x100 and x010 to be the disjoint union over all manifolds M and N of SK embeddings from M to N. Now, what do I do in this cobordism direction? Let's go sort of went into the page. So I have a boundary. So I have 3 boundary components of my cobordism, the ingoing, outgoing, and the free boundary. And I need 2 different types of colors in each direction. So I sort of do a similar construction as before, where I take these 2 colors, and then I take the co-limit of them going to 0. And then the way I define x001 is actually, so I have one, I want to have like so if I think about like a cobordism category, then I want to add cobordisms of length 0, which are the identities. You can also work with sort of non-identity and semi-simplicial space, but we've worked with next simplicial space, so we want to have degeneracy maps. So we just want to add, like as a disjoint component, all the objects, which are the identity maps or degeneracies. And then I take 0 to infinity, which stands for the length of my cobordism, times this moduli space of all cobordisms. Okay, so there's a lot to define in trisimplicial space. So x110 is a topologized version of my cut and paste square. So that's like the sort of front faces. So if I have such a square, it's in particular made up out of 4 maps. So this is a subset of x100 squared times x010 squared. And I topologize this as a subspace. And then on x101 and x001, I now want to define an SK embedding of cobordisms. Okay, so in particular, so I define an SK embedding of cobordisms that extends the 2 SK embeddings on the front and the back. And I get this image of the degeneracies. Now I'm finally ready to define a standard, like a cube of manifolds. So this will be a cut and paste square of SK embeddings of cobordisms. So I could also sort of visualize it instead of doing kind of based squares on manifolds, and now doing kind of based squares on cobordisms. And again, I can give this like a subspace topology. And now this is enough, I can define the rest of my trisimplicial space using admissal composition on faces. So whenever two cubes are sharing a face, then I can glue them together. So of course, if I take the realization of this trisimplicial space, I'll want to work with a diagonal. So it's good to note that this diagonal, you might want to think of as the nerve of a topological category, but we can't. So in order for that to be true, you would have to be able to compose two cubes that share one vertex. But that already doesn't work on the level of just squares. So here I've taken two squares that share sort of one vertex on the right spot, and I want to extend this to a 2 by 2 square. But I can't, like, even though these two are nicely defined push-out squares, I can't finish this push-out. So what happens here is that if I go from there to there, I'm gluing this yellow bit on, but I'm gluing it sort of on a new boundary that's here, but not there. So like, I can't say that I can't view this as something that I glued this thing and that thing over that thing. Okay. So we actually want to compute. We want to compute something about this trisimplicial space, right? So in order to make things computable, we would prefer to work with something simpler like a simplicial set. And it turns out that because I've taken discrete topology on my objects, or the vertices, it turns out I can take pi0 of this trisimplicial space, and this will have the same, this will be a two-connected map. So what I get is the pi0 of my k cubes, which by definition is pi0 of loops of the Svetli realization of the trisimplicial space. It's the same as, I'm taking out loops, so it's pi1, and it's pi1 of the normal realization of pi naught of this diagonal, which is just a simplicial set. Okay, so the theorem is that this pi naught of k cubes is SK bar boundary. So what we're actually going to compute is pi1 of the realization of pi naught of x, this diagonal x. Okay. So here I hope there's going to be some nice pictures that will, or at least pick some people up. So what's our method for this proof? So first I want to contract all vertices to one base point so that I only have one vertex. And then I can say that my pi1 is given by, because I'm just working with a simplicial set, generators are given by one simplices. So one simplices correspond to cubes. And relations are imposed by two simplices, which are 2 by 2 by 2 cubes. Okay, so how do I, just to have a little dictionary, how do I think of like these how do I go between a trisimplicial space and or trisimplicial set and just thinking of a simplicial space? So I can think of one cube as being a one simplex between the sort of the left upper vertex and the right lower down vertex. Okay. And then I think of a two simplex, which is 2 by 2 by 2 cube, as it goes from this yellow one simplex. Sorry, it goes from this corner. Okay. So I have to think about it as a two simplex in the following way. I have one edge is the one simplex, that's this first cube. One edge is the purple cube, and the whole cube if I look at it as a composite. So I just think of like the furthest away vertices. Then that's the composite of these two cubes. Okay. So if I think about it as like a nerve of a category or something, then you compose two morphisms, and that's the composite, and that forms like a two simplex. So in particular, as a relation on the one simplices, this gives the relation that's the yellow cube as a one simplex plus the purple cube minus the big cube, if I think about just the outlying vertices, is 0. Okay. So now, in order to like simplify the computation, I'm going to use a little bit of notation. So whenever I write brackets, then I think of completing this map to a cube, or to a two simplex if it's two composed maps. So for example, this bracket A goes into B is the cube where I have these maps, all the horizontal maps and identities everywhere else. And I can also do this on, like, I can pick a face and then I can extend it using degeneracies. So one little exercise in this that we're going to do first is how to contract the zero simplices. So I think about the map, the empty set goes to, like, it embeds into a manifold A, which embeds into a manifold B. And I think of this as a 2 by 2 by 2 cube. So I can also think of this as a two simplex that goes from like empty to A to B. And this will impose the relation that empty to A plus A to B minus empty to B is 0. Okay. So in particular, all of my, of course, for any manifold A or B, the empty set includes, like, embeds into any manifold. So I have sort of I have a one simplex from the empty set to any manifold. And then also whenever I have a map, an embedding from A to B, then I can fill in this two simplex. So that means that what I have here, I have a cone. So all manifolds, all vertices are connected to the empty set, and all the maps between them are as well. So I can contract this entire cone in the realization and get a space that is homotopy equivalent. So this means that all my vertices are going to be contracted. And moreover, I also contracted all of these horizontal hook maps. So now I'm working in sort of a reduced space in which I think of all vertices being the same thing and all horizontal maps as being collapsed. Okay, so now we're going to do some more gymnastics using this. So I can just pick some two simplex and let it tell me what relation it will impose. So here, for example, I've generated something like a 2 by 2 by 2 cube. Here I've just taken one cobordism, W0, and here I've taken some other at random some other horizontal map. And I get that the class of this cobordism, which is the blue cube, plus the class of the yellow cube, equals the class of the whole cube, which also corresponds to the green one. So in particular, this tells me that the one simplex that is generated from this W0 is the same or is equated to the one simplex that's generated from this upper face. Okay. So I get that something generated. So the class of W0 equals the class of some SK embedding from W0 to another cobordism. So now I can also like twist the cube around, use a very similar cube to rearrange this, and I get like the opposite equation, namely that W1. So the image, the target of my SK embeddings of cobordism has the same class as this square. So I have W1 equals the SK embedding from W0 into W1. Okay, so like just putting these things together, I have that the class of something generated, a one simplex generated by W1 is the same as the class of a one simplex generated by W0 whenever I have an embedding from an SK embedding from W0 into W1. So one particular cobordism that is nice that maps into any other cobordism is the empty cobordism. It goes from the empty set to the empty set, and it's empty, and it has a certain length L. So in particular, what I just said tells me that any one simplex generated by cobordism is the same as the one simplex generated by the empty set. Okay, so I've not been telling you what lengths the cobordisms had. Like all of our cobordisms had a certain length, and my SK embeddings were only allowed were supposed to preserve that length. So just to remind you, like I had this disjoint component that was like the objects or the degeneracy maps. But these also are mapped to degenerate one simplices, so they have to be 0. And then here, well, I had this length parameter, but it was in a continuous interval. So and remember that I've taken pi naught of my diagonal. So that means that this entire thing is contracted in the sense that I just have one length for my cobordism. But if I compose my cobordism with itself, then it becomes twice as long. But that means that it's still the same length because I only had one length. So what I conclude is that like all my cobordism one simplices, which were all the same as just the empty set with a certain length, are all 0. So all simplices generated by cobordism are 0 in pi1. Okay, so let's do some more interesting relations. So now I'm taking a generic one simplex, which is the red one. So this is just some cube of manifolds with 8 different manifolds in it. And by extending by the identity in sort of the downward direction and the leftward direction, I can build a 2 by 2 by 2 cube, which is going to give me a relation. And what is this relation? Well, it says that's the blue cube, which is A going vertically to C, plus the yellow cube, which is generated by this horizontal square, is the same as the whole cube, but that is the same as this red cube. So it's the generic. And now this horizontal square, this is a class generated by an embedding of W1 into W2, the W2 into W3. So this was, as I showed before, the same as just generated by one of the cobordisms. So this is all 0. So I get that the generic simplex is can be represented by the vertical map A to C. in pi1. So rearranging this slightly, I get a very similar statement for that it can also be represented by the last map, the last vertical map, B to D, B prime to D prime. So that class is also equal to the generic one simplex. So I have a generic one simplex. I can either represent it with the first vertical arrow or with the last vertical arrow. And now I take sort of the 2 by 2 by 2 simplices that are generated from a cut and paste square ABCD in two different ways. And this tells me that this cut and paste square is also the cube coming from a cut and paste square can also be represented by either A goes to C or B goes to D. So here I had B prime going to D prime, so that it was if I had a cube and I was also going in the cobordism direction, but here I can sort of take two of the front vertical maps. Okay, so I can also use, so if I have a map A to C, then I can also take an embedding of the empty set into A. And if I take the boundary of this, I get that like A to C, which is the last bit, is 0 to C, which is the whole composite, minus the empty to A. Okay, so I can now think of all of my generators as empty sets going into a manifold. So I represent this by just writing the class of the manifold. So now I've reached a point where I'm identifying the generators of my pi1 with manifolds. So I have sort of reduced all of this was in order to like get down from a cube, which was 8 different manifolds with all these different maps. And I've now said, well, I can represent that by just one manifold. Okay. I'd also shown already that this, like a cut and paste cube, can be shown it equals both the first vertical map and the last vertical map. And if I rewrite this in this language, I see that this is actually saying C minus A is D minus B, which is exactly my square relation. Okay, and we'd shown before in the previous paper that the square relation is equivalent to saying that the manifolds are up to SK equivalents. So I've now reduced to saying that my generators for pi1 are manifolds, and the SK relation is one of the relations on them. Furthermore, if I now take this sort of side face of a cube and I extend it into to a cube, then I get that cobordism manifolds are also in the same class. And now I think maybe I won't say this, but so I can also easily show that a generic 2 simplex reduces to only these relations. So you don't get any additional relations from taking a generic 2 simplex. Okay. So this sort of concludes the details of that proof, which I thought I would show this time. So I've now shown that like pi1 of this realization of the simplicial set indeed corresponds to manifolds up to SK relations and cobordism. Okay. So now I have this trisimplicial space x0 x dot dot dot, and there's 2 interesting sub-simplicial spaces of this. So the first is that if I take x0 0 dot, so we've already seen it like going into the page, we have cobordisms, and indeed if I just take only this simplicial direction, I get the nerve of a cobordism category with trivial boundary. However, as we've also, so we just went to the proof and we saw that all of the one simplices that are generated by cobordism are all 0 in pi 1. So even though we do get a map from loops of the cobordism category to k cubes of the manifolds, this does not sort of yield an interesting map on pi 0 or k0. But in principle, it could be an interesting map on higher multiple groups. So another interesting subsimplicial space is x dot dot 0. So this is just taking the front sort of faces and looking at what squares can be built out of that. And this is a topologized version of the bisimplicial set that I had before. So this is topologized SK squares. So what we can do is we can also the previous spectrum that we defined. We can define a topologized version of this by taking loops of the factorization of this topologized bisimplicial space. And we show that again on K0, we get SK boundary out of this. And now there's a very natural map coming from the inclusion of this simplicial object from K squares of topologized manifolds to K cubes of topologized manifolds. And this lifts very clearly on pi 0 the canonical surjection from SK boundary to SK bar boundary. Right, so that was a lot of details, but I hope you're interested in our work, and you can read other stuff in our papers. Thank you.
Yeah, thank you very much, Renee. Nice talk. Yeah, the second time I see it. Well, is there any questions? Just unmute yourself or write in chat.
Wow. Does this complete your study, or do you have more things in mind?
We have many more things in mind. Yeah, so one interesting direction is that we want to find a lift of the signature map to L theory, and also understand better this relationship with cobordism, because it would have been nice to find a lift of the map from cobordism groups to SK bar, but we found some map from cobordism, but it doesn't. It doesn't lift this map on groups. So it'd be interesting to understand more about that.
Mm-hmm. Are there some simpler cases that don't involve you in so many details as you had to give here? That's still simpler cases that still have interest.
I mostly I sort of presented this because I heard that many people would have been at the talk in Oaxaca, and where I sort of gave a bit more of a superficial talk about different things. And I think it uses a lot of the input that's used a lot for cobordism categories. So usually I think people, yeah. But we do really need a topologized version in order to define our cubes. And the reason is, like, if we want to define these embeddings of these cobordisms, we really need to, like, we can't take a diffeomorphism class of a cobordism. We need to, like, be able to define what the map actually is, and otherwise yeah.
Okay. Thank you.
Renee, I do have a question, or maybe just a comment. I studied the classification of coverage categories, but then for the G-coverage case, I define the SK coverage category. So you have the same coverages, but then just you look at the SK equivalent relation, and then you obtain a category. And if you study the fundamental group of that category, this is just the Bogomolov multiplied plus a copy of the integers. So I
didn't quite catch that. Like if you take what into account, what category?
So you take the same coverage category equivariantly. With
Equivariance, yeah.
Right. Those over all spaces, and you quotient, or you put the equivalent relation of S Schneiden-Kleven, and then you obtain the direction of the Bogomolov multiplied plus the integers. And so the calculation is quite similar as yours. And I saw in your talk that you work with a trisimple set, and with that, I don't know.
Sorry, you cut out, so I didn't see. I didn't hear the last couple minutes.
Yeah, my question is just why not to work with a cobordism category just with some Schneiden-Kleven relation, like in Galatius, Mass, and Tillman Weiss.
Yeah, so like we've taken like group completions, and like pi naught of such a cobordism category would be a monoid. If we take like a trivial boundary cobordism category, for example. Now we thought about this framework of K theory, which is why we really need the boundary. Yeah, so I haven't thought about, but yeah.
Yeah, maybe it's not a double category; it's a triple category or something like that.
I think I don't quite know what you have in mind, but I'd be interested to like talk more about it.
Yeah, it's just to have the same cobordism category that work Galatian, Mass, and Tillman, and Weiss. But looking the Schneiden-Kleven relation there, and in some sense you have.
But how plug it in? How like? You quotient manifolds and bordisms by it or something, or I wouldn't know how to do that with like.
So in a sense, this is what's going on here, more or less, but there are two types of cuts that's going on. One corresponds to composition direction of cobordisms, and another is very restricted cut where it's cylindrical cut. So in a sense, we are doing cut and paste on cobordisms with boundary, but not formulating it in a way that we work just with category of cobordisms, but we introduce these two directions to say how cuts can look.
Yeah. So we showed in previous work that like taking squares of manifolds is equivalent to working with SK boundary. So now we're sort of taking squares in the category in the cobordism category.
Yeah, thanks, Renee. And maybe it would be great to develop the equivariant version and also the stratified version. It's Schneiden-Kleven with stratifos. Well, is there any other comment, questions? Well, thank you very much, Renee.
Thank you again.
Thanks for inviting me.
Very fascinating.
In 2 weeks, we have the talk by Carmen.
Yes, my turn.
More.
Also in Sniding Clever.
Yes, more. By the way, Carlos, I am thinking a little bit about, well, this is another project that I have to retake, the equivariant cutting and pasting. And the in particular, probably you might have heard about SKK groups, which didn't feature in this talk. It's like the refined version. So this is another project that those groups are one interpretation of vector field Bordism. And now when you go equivariant, and you have some group action, it's a little delicate, but the question is, do you actually get an equivariant version of vector field Bordism? When does it match equivariant SKK and when does it not? So that's something it's a project that's like, for me, it's halfway through and I have to finish it. But, it's one of the many questions you can ask. And it's you said equivariant. Yes, equivariant is an interesting thing.
So there's a couple more. I think we have various projects also in an SKK direction.
Yeah.
And so I'm also like looking at like certain like SKK groups, and we're also like with the new methodology, we'll look at sort of a stratified or nested version, sort of like of these SKK as well.
Yes.
Which then will hopefully also like, I mean, it will naturally provide more SK groups with substructure as well, with additional structure.
Well, really nice work. Yeah, three of you. And we hope to see you here in Oaxaca.
Yay! Wait to get to Mexico. I'm so excited about it.
Yeah, next time you have to come. Yeah, well, yeah.
Yes.
Carmen.
Okay.
Well, thank you very much to everyone. Yeah, so see you in 2 weeks. Yeah.
Okay.
And, have a nice weekend.